Welcome friends. In this video we will be discussing about local linear approximations. Now the basic concept of local linear approximations is that any continuous function can be approximated by a straight line in a very small neighborhood of a given point. So first, before we move on to functions of several variables, we will just rewind local linear approximation in case of a function of one variable. Okay, you can see this figure here. This is the graph of the function y equal to x square plus 1. If I take a very small portion of this graph, which you can see here, it is magnified. Now that almost looks like a straight line. This property is there for any point on this curve y equal to x square plus 1 because it is continuous. You can look at this point here. If I zoom that point again, it looks like almost like a straight line. So all these points you can see, even at this point where it is having a bend, if you zoom quite enough, it will look like a straight line. Okay, so this property can actually be used to approximate the value of that function in a small neighborhood of a given point. That is, any nonlinear function can actually be approximated by a linear function in a very small neighborhood of a given point. Now theoretically speaking, what we are going to do is we will just first write down the equation of the tangent at a given point. So suppose we are having a point x1 y1, we know the equation of the tangent is y minus y1 is equal to m into x minus x1. So at a given point a f of a, the equation of the tangent will be y minus f of a is equal to f dash of a into x minus a. So y is equal to f dash of a into x minus a plus f of a. So this f of x can actually be approximated as f dash of a into x minus a plus f dash of f of a in a very small neighborhood of the point a. Okay, so this is called the local linear approximation of the function. Now we will move on to functions of several variable. But before that, just look at this example here. Now here we have just wrote down the local linear approximation of root x. Function of one variable is not part of the syllabus, but we are just discussing that in a go. Okay, so f of x equal to root x. The local linear approximation will be root x is equal to 1 plus 1 by 2 into x minus 1. So if you want to find an approximate value of root x at the point, say x not equal to 1, you can use this linear function 1 plus 1 by 2 into x minus 1, or in some complex scenarios, if root x comes, then you can actually simplify that equation, non-linear equation, into a linear one using this expression. But you must understand it is just an approximation. It will involve an error. Okay, so this can serve as an approximate value of root x. Now we will move on to functions of several variables. Now in function of two variables, if f of x was f of xy is differentiable at the point x naught y naught, then f of x naught plus delta x, y naught plus delta y can be approximated by f of x naught y naught plus fx into delta x plus fy into delta y. So if I'm taking this first point as x naught y naught and the second point this x naught plus delta x as x and y naught plus delta y as y, f of xy can be approximated as f of x naught y naught plus fx into x minus x naught plus fy into y minus y naught in a very close neighborhood of this point x naught y naught. So this expression that you see here is called the local linear approximation of f at x naught y naught. So L of xy is f plus fx into x minus x naught plus fy into y minus y naught. That is the local linear approximation of the function f at the point x naught y naught. And the error in approximating this f of xy by L of xy will be less than the distance between the points x naught y naught and x naught plus delta x comma y naught plus delta y. This property we will have to illustrate in the coming problem. So let's look at this problem here. The question is, let L of xy denote the local linear approximation to f of xy, which is given by square root of x square plus y square at the point 3, 4. Compare the error in approximating f of 3.04, 3.98, which is equal to square root of x square plus y square, that is square root of 3.04 square plus 3.98 square by L of 3.04, 3.98, with the distance between the points 3, 4 and 3.04, 3.98. So first we will just find the local linear approximation. Okay, so we are given with f of xy is equal to square root of x square plus y square. Okay, so what is fx? Fx is 1 by 2 root x square plus y square into 2x. So 2 will get cancelled. We are left with x by square root over x square plus y square. Now fy similarly will be y by square root over x square plus y square. Now local linear approximation L, we know that is equal to f plus fx into x minus x naught plus fy into y minus y naught. Okay, here x naught y naught is the point 3, 4. So 3, 4. We have to evaluate all these values at the point 3, 4. So what is f of 3, 4? F of 3, 4 is square root of 3 square plus 4 square, which is 5. What is fx of 3, 4? Fx of 3, 4 is x by square root of x square plus y square, that is 3 by 5. Okay, what is fy of 3, 4? Fy of 3, 4 is 4 by square root of 3 square plus 4 square, that is 4 by 5. Now let us substitute all these points into the given expression of L. Then we have L is equal to f plus, so f the value is 5 plus 3 by 5 into x minus x naught plus 4 by 5 into, sorry, x naught is 3, x minus 3, 4 by 5 into y minus 4. So this is the local linear approximation of the function at the point 3, 4. Now they have asked you to show that the local linear approximation is less than the distance between the points, say 3, 4 and 3.04, 3.98. Okay, so that is what is shown here. Now first we will see L of xy is the same thing that we got here, 5 plus 3 by 5 into x minus 3 plus 4 by 5 into y minus 4. Now they have asked you to use this, that is use the value of L of 3.04, L of 3.98 to approximate the value of f at 3.04, 3.98. So this is approximate value of f. We have this function with us, but usually we are actually trying to find the approximate value of this function. Okay, so we have the actual value of f at 3.04, 3.98, which is this value here. Now the approximate value, that is the local linear approximation, is L of 3.04, 3.98. They are saying that this difference, that is the error between L and F, will be less than the distance between the points 3, 4 and 3.04, 3.98. Okay, so first, what is f of that is local linear approximation? Local linear approximation is 5 plus 3 by 5 into this 0.04, that is difference between x, that is 3.04 minus 3 comes out as 0.04. Okay, plus 4 by 5 into, we have 3.98 minus 4, which comes out as minus 0.02. So L of 3.04, 3.98 comes out as 5.008. I hope it is clear. First we are finding the local linear approximation at the point 3.04, 3.98, which comes out like this: 5 plus 3 by 5 into 3 minus 3.04 plus 4 by 5 into 3.98 minus 4. Okay, so which comes out as 5.008. Now the actual value, the function we are having it with us. So the actual value is square root of 3.04 square plus 3.98 square, which is approximately 5.00819. Now this is the local linear approximation at that point. This is the actual value at that point. Now the difference between these two is the error, and that is 0.0019. This is the error. Now, what is the distance between these 2 points? That is square root of 3.04 the whole minus 3 the whole square plus 3.98 minus 4 the whole square. That is what is given here. Distance between these 2 points, and it is 0.045. So this error is very much less than the distance between these 2 points. So that is what we have to illustrate last. Okay, we have illustrated that the error is actually very less than the distance between the 2 points. So what we are actually doing is we have found the local linear approximation at this point, and then we have found the value of 3.04, 3.98, that is L of 3.04, 3.98 as an approximate value of f of 3.04, 3.98. Now the actual value, we have it with us. So the difference between the actual value and the approximate value is the error. So the error is very much less than the distance between the 2 points, 3.34 and 3.04, 3.98. Thank you.